Okay, so last time we talked about, why are we using Hess's law, this method of using the series of steps rather than trying to just do the entire reaction in the lab and gather the data there. Talking about how a lot of times, unless you have really good insulated equipment, a good colorimeter, then it's really hard to get accurate measures of the delta H. So since there's all these published values of scientists and chemists in the past that have done these at standard conditions, we can use that information that's published, and there's a reference table in the back of your textbook in the index area, reference area, that's going to have the delta H's. It also has the delta S's and or the S's and the delta G's and stuff in there as well. So there's lots of information, published data that you can use in order to calculate delta H. So Hess's law basically that if it's carried out in a series of steps, the overall delta H will be equal to the sum of the enthalpy of the individual steps. So you can use the published data and calculate delta H that way. This energy diagram over here showing you the increase in enthalpy. Your enthalpy, this is your heat, there's your products heat, here's your reactants heat, much higher amount in the reactants, okay? Showing you that if you did the combustion of the methane with oxygen in the lab, okay, and you measured it, you should get this negative 890 kilojoules being released. But since it's very hard to measure that, especially with our equipment in our lab, you could look up the published data here of the two steps here and take a look at these reactions, and the one that's going, there's got to be another intermediate one that's not up here, but because the methane would be a part of it. To get your overall balanced reaction, they're giving two delta H values with a series of steps, and you can add them together and get that negative 890, okay, and still get the enthalpy for the combustion of the methane. Okay, so it's a state function. We're looking at the, here's your initial, here's your final. The difference is what we need to find there. The final difference between the two will give us the change in enthalpy. So it really doesn't matter if we're looking at it over there in the pink with the steps, or if we're just doing the direct one-step reaction. And like I said, for this one, for our purposes, we use Hess's law a lot because it's just really hard to measure. All right, so let's look at this example. This is a very simple reaction. Delta H1 there is representing the delta H for the entire reaction. So we're not really doing a whole lot with this except for looking and examining it. There's series of two steps here that we look up in the published data with their own delta H values. You have nitrogen plus oxygen giving you nitrogen monoxide. You have nitrogen monoxide plus oxygen giving you nitrogen dioxide. And each one's been measured for their enthalpy change, and it's found in the index or the table, okay? So what we're doing here then is we want to get that overall reaction at the top, this guy up here. We want to get this reaction out of our series of steps. So we have our series of steps, and we want to create that overall reaction. So what you do is you look for the overall reaction. Where's the nitrogen? That's the first reactant. In our series of steps here, do we have a reaction where nitrogen's a reactant? Yes, it's right here, right? Okay, so that's good. That matches up. How about over here? The next reactant is oxygen. We have, in both of our steps, we have an oxygen molecule, so that's good. And then what do we want as our product? Nitrogen dioxide. So this is the one we want as our product. So just as long as our series of steps are matching up, we do want to have the same number of moles. Their coefficients need to match. Okay. What do we notice about the NO though here? The nitrogen monoxide. Well, it's a gas, okay, but looking at the series of steps, what's interesting about where it's located? It's on the reactants of one and the products of the other step, right? When we have that in a series of steps, guess what happens to them? They do cancel out, okay? Okay, they're going to cancel out like so. When they cancel out, we create our overall balanced reaction that we have up at the top there. And in order to calculate calculate the delta H, okay, all you have to do is add the 2 delta H's there of the steps in order to get your overall for the reaction. This is a very simple one because we didn't have to flip or multiply on it. We're going to show you ones where you would do those steps in order to line everything up. Any questions? Okay. So we end up with our overall. Now, if a reaction, you have a series of steps here. If you have to reverse one, this is what you do. You change the sign on the delta H. So that's one thing that you can manipulate when you're doing Hess's law, is you can reverse a step and then you can change the sign of the delta H. The next thing that you can do, and you probably shouldn't have to write all of this down, but okay, the magnitude of the delta H directly proportional to the quantities of the reactants and products. You don't probably need to write that sentence down. What you need to note though about that is that the coefficients in front of the reactants and products, you can multiply them by factors. But if you multiply an equation by like a factor of 2, then you would also have to multiply the delta H by that factor of 2. Because remember, it's extensive property, so if you're changing the amounts, you would also change the amount of the delta H. So, if you're multiplying and changing coefficients by multiplying through, also multiply the delta H by that exact same value. And by doing these 2 steps, or these two strategies, we can manipulate the steps to reach our overall balanced reaction and then calculate our delta H at the end by adding what the result is. Okay? So one thing you can do, reverse, change the sign. The other thing you could do is multiply by an integer, but also multiply the delta H by that same integer. Okay, so make sure that you understand those 2 strategies. And then, of course, I have the some other strategies there where to start when you're looking at a Hess's law problem. They look kind of scary because they have all these steps and numbers and stuff to them. They're really not that scary. Okay? So, problem solving. First thing you should do is look at your overall balanced reaction so that you can work backwards from it. Line up the reactants, line up the products, look at the coefficients. I always start with the balanced reaction and work through my steps that way. Okay? The other thing, you can reverse as needed. We just said that one. And if you need to, you can multiply as needed. Okay? So let's take a look at the next example and work through it. Example 2 here. Consider the following data. These are our 2 series of steps. And yes, it looks a little different because now in AP you were always told, oh, the coefficients always have to be whole numbers. Well, you're going to see these with the fractional numbers in front of them. And that will happen through the heats of formation as well. You'll see these fractional coefficients. It is allowed, okay? These are our 2 steps. These are their delta H's, but we want to achieve this overall reaction. We want to achieve nitrogen, 2 nitrogen molecules plus 6 oxygens, 6 waters, 6 waters, giving us 3 oxygens and 4 ammonias. That's our overall. So I'm going to start there and start looking at my steps. Okay? So here I have nitrogen. Where is nitrogen in my steps? Oh, it's right here. Is the nitrogen on the correct side of the equation? No. So what am I going to need to do to that equation? I'm going to need to flip this one, right? This one's going to need to flip. If I flip this one, then what happens to the sign on that? It changes to a negative, right? Negative 46, right? How about looking here now at my next reactant, my waters? Where is the water located in the series of steps? It's right here, right? And it's in the products of the steps. So what am I going to need to do to that equation? Also flip this one. By doing so, this becomes a positive, right? So that's the first thing I need to do is look at that. Okay, so go ahead, we're going to rewrite them in a minute, so give it a moment here. We're going to flip both of them, but we start looking at their coefficients, they're not accurate either, right? So let's do that. Okay, so now they're flipped, but looking here, we need 2 nitrogen gas molecules Okay? What do we need to multiply that by in order to get that to be a coefficient of 2 now? We need to multiply that by 4. Okay? So we're going to multiply that one by 4, like so. But if we multiply the equation by 4, we also multiply the delta H by 4. Looking at the second step with the water there, it's now on the correct side. But instead of 2 waters, we need 6. So what are we going to multiply that equation by? 3. So we're going to multiply that one by 3. That means we also multiply the delta H by 3. So go ahead and take a moment to do that. We are trying to achieve this overall desired reaction at the bottom. We want that form to be formatted this way. Okay. Yes, we need 2 nitrogens plus 6 waters, giving us 3 oxygens and 4 ammonias. So 4 times the negative 46, multiply that. Now, what I do is I rewrite the equations at this point with their correct coefficients. I write their new delta H's over here. Here's our new delta H's that have been multiplied, and the signs have been changed because we flipped them both. So I rewrite them, and then I look because I want to make sure that I'm getting my overall balanced reaction and I'm canceling appropriately. What you should notice is we have hydrogen here and hydrogen here. 6 hydrogen are a reactant, 6 hydrogen are a product. When you have them on both sides like that, what happens to them? They cancel. Okay, so you would cancel those out like so. Now, then you should check to make sure everything else is in its right place inside the reaction. So the nitrogen here, okay, it's in its right place. It has the right coefficient. Let's look at the water. It's in the correct place. It has its coefficient of 6. Then we have the 4 ammonias. It's a product and it has the right coefficient. And then our 3 oxygens, we check that. Everything's in its correct place, ready to go. Then all you have to do over here is add it all up. Add it all up, and what do we get for our delta H? What do you get there? It's like positive what? 1,268 kilojoules. Very good. And that would be correct. There we go. There we have it. Now, this one only had 2 series of steps to reach its overall desired reaction. The next example that you're about to look at has 3 steps that you'll have to manipulate and look at. So I'm going to give you like 5 minutes or a few minutes to look at that and try to work it out. Then we'll go over it. Question? What? What we multiplied through the 4 on the top, we also multiply the delta H by that 4 as well. Alright, so here's your next example. There's your overall reaction. I did it in the pink color, purple color up there. You have a series of 3 steps to look at. Okay? So try it real quick, see what you can come up with. Okay, so let's look here at our first step. We have, yes, we do have 2 that have fluorine in it. So I would encourage you to wait on the fluorine and look at other stuff first, because since there's fluorine in 2 of the steps, they will probably work themselves out if you're looking at the other components. So I'm going to start here and I'll look at, say, the HF, because that's in my overall reaction. And it's in its correct position, right? It's in the products where it's supposed to be. But does it have the correct coefficient? No. So what must we do to that one? We need to multiply this one all by 2, right? So then I rewrite it here because I like to cancel. My delta H, though, now gets multiplied by 2, and it ends up being negative 1,074 kilojoules. So that one should be correct now. looking at this one, I'm going to match up my CF4, which is up here, okay? Does that one need to be flipped? No. What do I need to do, though, because of the coefficient? So I'm going to multiply this one also by 2. So I do that. Then I get 2C's plus 4 F2s is going to give us 2 CF4s. My delta H also gets multiplied by 2, so negative 1,360 kilojoules. Good. The last equation here. We need to match up the ethene here, C2H4, but it's over here on the reactant side. So what do I do to that one? I need to flip it. So this one I flip. The coefficient's fine, so I'm just going to flip it. Oops, no plus here. We need to go to our products. But I changed the sign on my delta H over here, so it's going to be negative 52.3 kilojoules. Good. So far, so good. Now, before I add up my delta H's, I'm just going to cancel and merge and make sure that I'm getting my overall balanced reaction. So if I look here, there's an H2 right here on the reactants and an H2 on the products, but there's no H2 in my overall balanced reaction, so you know these are going to have to cancel, right? What else is going to cancel? The carbons. Remember, there's a product and a reactant. They cancel out too. Now, I see my C2H4s here. I see my CF4s here, and my HF. My fluorines, though, there is a couple of them on the reactant side. What should I do with those? I should just add them together. So that's a total of 6. So I do end up with 6 F2s, which is what I want up here. Okay. And then my 4 HFs and my 2 CF4s. Okay, so does it match now with the canceling and everything? Good. Now all I have to do is take these values and add them up. Okay, so our calculator answer when we add them is going to be different than our sig fig answer, but we're going to check that. So I get 2,486.3 negative kilojoules. Now this is an adding problem, and what's the rule for significant figures when we're adding? We're looking at place values, and this one, the place value is the ones, this one's the tens, and this one's the tenths. So what should we round to? The tens. So here at the 8 is where I look for rounding. So 2490 kilojoules, correct? Yes, the least precise place value would be the tens there. Okay, remember looking at the precision of the place value when you're adding and subtracting. So this would be our final answer for this one up here. Okay? Any questions on that?